want to take a moment to introduce arrow pushing. And so in organic chemistry, we know that a negative charge is going to mean an additional electron. So whenever we have a negative charge, that means an additional electron. And so we also know that an arrow movement represents the movement of two electrons. A single-headed arrow is the movement of one electron. Now, this is all convention, but we have to understand what's going on when we present the symbol of arrow movement. We're moving two electrons from one place to another. And then when we have a single-headed arrow, it's going to be movement of one electron from one place to another. Now, they can also go in opposite directions. It's also not just one direction, but they can go in the other direction as well, or in any direction, actually. But just recognize, again, the significance is two arrows are being pushed around, or one arrow, one electron is being pushed around with a single-headed arrow. Now, let's not mistake an equilibrium arrow for a resonance arrow. Resonance arrow is a double-sided arrow. These two are not the same. One is essentially a different arrangement of electrons, which is our resonance. The other is showing that there is an equilibrium between the reactants and the products. Now, convention tells us that we have to move always from electron-rich to electron poor. And so what does that look like? That looks like a negative charge over to a positive charge. It could be a negative charge over to a partial positive center, right? It can also be a lone pair over to either a positive charge or a partially positive center, right? So it can move here or essentially there. So I'll just connect the arrows. I don't want to do that so as not to confuse you, so I'll just go ahead and create another structure and redraw the arrow, right? So here again, electron rich. In this case, these are lone pairs. Lone pairs are electron rich. And then here are full negative charges, right? Now, remember what we said about negative charge? It is representing an additional electron. Now, there's two ways to represent that additional electron. One, you can actually show which atom it's on by drawing it above the atom. So we know that the additional electron in this Lewis structure, right, is going to be actually on the oxygen. Now, if I write out CH3O minus, and we write the minus, we don't know exactly from that structure. We can assume, based off knowledge and experience and what have you, doing a bunch of these problems, that it's going to be on the negative charge. But essentially, this is saying that the overall molecule overall is charged. And this is saying that the charge, the additional electron, is on the oxygen. Right? And so keep those two in mind and understand it. Now, we're going to go ahead and do what's an incorrect arrow movement. And I'm going to explain also why it's important. So I see students doing this all the time. They, at least at the very start, they move things from opposite. So they'll say, okay, here I know that OH is typically positive, or the H is typically uh, electron. So let's say this is CH3. They try to move the H over to a positive, right? You can't do this. You can't do a positive charge to a negative charge. You can't do something that is essentially not electron rich, which is this bond, because again, the electron richness is residing in these lone pairs, right? And have it move over from the hydrogen to the positive charge. Oftentimes, students, what they mean is this, right? But they mistake it for this up here, this figure up there. So again, don't make this mistake of drawing it from a hydrogen or proton to a positive charge. Again, this proton right here is actually closer to being electron poor. So it's like moving a partially positive to a positive. So we never do this. We always move from lone pairs to positive charges. And then I'll go ahead and add on here. Let's do lone pair to maybe something that's acidic. So let's just do oxonium. And right, and we can have that happen. So again, electron rich, the lone pairs, to something that's electron poor, which is the hydrogen. Why is the hydrogen in this case electron poor? So let's take a look at water. Water has a dipole moment, just like the oxonium molecule up here, right? What's happening is, because oxygen is a little bit more electronegative, what we end up getting is a partial negative on the oxygen, a partial positive on the hydrogen. So again, this hydrogen becomes electron poor. And so these lone pairs, they essentially attack that hydrogen. Now, one more thing to add is that this is super important because of two reasons. The first reason is that you might have 1 point taken off each quiz exam just because of wrong arrow movement. Over time, that adds up 5 points, 10 points, so on and so forth, right? The second reason this is super important is because, and I mentioned this in a different video, it really points out the students who don't know their stuff. If I see a mistake where the person's moving the positive charge, the electron from a positive to a negative, I immediately know that they really don't have a good grasp of the material. I mean, this is such a basic thing that we'll do again in practice over and over and over, moving electrons around, that if they make this mistake, I can tell that they have not done the reps necessary of arrow pushing, resonance, structures, mechanisms that is required. So what that immediately triggers in my mind is, I know the student really is not performing well, and it almost opens my eyes to other mistakes that they make, or at least makes me aware that this person probably has a lot more mistakes. So subconsciously, whether I'm aware of it or not, as a grader, a TA, a professor, I'm actually looking for more mistakes, and then you're going to end up finding more mistakes. Whereas if another student had most of the foundations right and it looked pretty good, it would be like you would almost trust it a little bit more not to find or not to look for a mistake. Now, again, this is unintentional. It's not like somebody's like, oh, I like this person, he knows his stuff, so I'm just going to go rounded to an A. It just means we're less alert to mistakes when the vast majority of the fundamentals, the foundations are right. When the foundations are completely off, you're going to be like, wow, this is going to be a pretty easy grade, a paper to grade, because there's just going to be so many mistakes, and you're going to just go through finding one after the next after the next. It's not necessarily fair, but again, it's a bias of having something so fundamentally wrong as arrow movement. And again, it's fundamentally wrong because the amount of times for you to solve problems requires so many arrow movement from negative to positive, as is convention, that if you get that wrong, it means you did not do the work, and it means you probably don't understand much of the material.